Hello, good morning to all the participants. So I welcome you here in the fourth day of FDP of Deep Learning, which is organized by E&ICT Academy. So now in this fourth day, the first session that will be taken by Dr. Vikas Kumar, and thereafter that I will take the session on the encoder decoder. So before start the session, let me introduce Dr. Vikas Kumar. Now, Dr. Vikas Kumar is with us. Dr. Vikas Kumar is an assistant professor in the Department of Computer Science and Engineering at Malviya National Institute of Technology, Jaipur. Before joining MNIT Jaipur, he served as an assistant professor at Shiksha Anusandhan, University Bhubaneswar, in the same department. Dr. Kumar earned his MTech and PhD in Computer Science and Engineering from National Institute of Technology, Patna, and his BTech from Maulana Abdul Kalam Azad University of Technology, Kolkata. Dr. Kumar research primarily focuses on intrusion detection systems, cybersecurity, network security, and machine and deep learning application to enhance security measures. Throughout his academic career, he has significantly contributed to cybersecurity, publishing numerous research papers in reputed journals and conferences. Additionally, he is an active reviewer for various esteemed journals such as the Journal of Supercomputing, Wireless Personal Communications, and Security and Communications Network. His recent works include advancement in machine learning techniques for cybersecurity and innovative applications of generative adversarial network in intrusion detection systems. In addition to this research, Dr. Kumar is dedicated to teaching and mentoring students, fostering a deep understanding of computer science and its application in the modern security challenges. His expertise and commitment make him a valuable asset to the academic community at MNIT Jaipur. So, thank you, Dr. Vikas, being with us in this FDP, and he is also a coordinator of this FDP, which is organized by the E&ICT Academy. Now, I am hand over the session to Dr. Vikas Kumar. Now, please take over the session, sir.
Thank you so much, sir. Thank you so much for the brief introduction, brief and nice introduction. So, good morning to all of you, the participants and the co-coordinator. So, today we are going to basically talk about the LSTM, the long short-term memory. So, let us start with the introduction. I think Dr. Surendra Han sir has already taken the session on this RNN. So I will just brief you about this RNN, then gradually we will move to the LSTM. So let me just share my screen. So I hope my screen is visible.
Yes, sir. Visible, sir.
Yeah, thank you, sir. So let me control the PPT. So the PPT is also visible.
Yes, sir. Visible, sir.
Okay. So good morning, one and all present here. So we are going to talk about the long-term short-term memory today. So before moving ahead, let us just briefly recap what you have already gone through in the previous lecture on RNN taken by Dr. Surendra Hans. So basically, if we talk about the RNNs, the purpose of this RNN is basically just a minute. So basically, if we talk about the RNNs, so basic motive behind the RNN is the the processing of sequential data. Okay. So now, whenever we talk about the sequential data, uh, do we mean all the sequential data, or are there any specific subset of the sequential data that needs the RNN to be deployed? So let us first go through one example. Just suppose, let me just write it here. Uh, Suppose I have one example. Just I'm writing here that and the another example is the same statement can be written like in 2023 I have visited Jaipur. Now both these two statements are same. It is true. Okay. Now the thing is, from these statements, suppose I want to train a model, any ML model or DL model we are trying to train. I just going to provide this as input, this set of statements as input, and we are trying to figure out either some we are trying to predict some value, or we may try to figure out, or we are trying to figure out the context. Okay. Now in these two statements, suppose we just want to highlight this 2023. So we want to know when I was in Jaipur. Okay. So if we talk about in terms of that already have gone through the feed forward neural networks. Okay. So in case of feed forward neural network, what will happen? So suppose we have a set of input, that is input your hidden states or layer, better say layer, not a state, uh, and then we have output layer. Now what we do generally, we provide this. Suppose we are having different neurons, so definitely we will be having uh, different weight connections. So if we talk about the weight, suppose this is another neuron, same way we may have this one. Now the thing is, here we are having a weight vector. So we all know, we have you may have talked about this in simple term. If we talk about the perceptron model, it was something like the weight into x plus bias. This was the simple model. Okay. So we are starting with this model only. Now if we talk about this w, and suppose we are having various neurons here, various input here, and then in the hidden layer it may be multiple layers, a stack of layers, or a single layer. Now from here we may have again the same thing, same way we can have different uh, so something like this. Okay. Now So this is W1, this is W2. Now the thing is, if we want to learn the context of this 2023, so suppose this will be the input vector. This will be our input vector, where it will be like I have something like this one. Now, if it whenever we talk about the feed-forward neural network, the thing is, first we cannot directly feed this data into the network. So first we need to transform it in the form of vector, the embedded vectors. That is the numerical representation for each word. So the embedding is not concern of this lecture. Just we are concerned about the learning of the context. So basically, suppose we are providing this vector into this network. Okay, what will happen is, so suppose this I will get through the first neuron, have visited, and likewise each of them is going through the input neuron to the hidden layer. Now just think that second time we are feeding with this input. So what will happen then? What kind of analogy will be there? So basically here what will happen is, this W1, what it is going to learn is, so first time this 2023 is at the bottom, or we can say at time step t equals to some what we can say 1 2 3 4 5 6. So at t equal to 6, while whenever we are providing this statement as an input, so this will be at t equals to 2. Now if I represent this W1 as weight matrix, so it will be something Wi to Wn, that is n cross 1 matrix, where n is the number of input feature. Okay, now, and if we break it down, this Wi is again, so if we talk here, if we talk about a single neuron, so just check here, from the single neuron, the weights are, for the same input I, the weights are going to be applied on that I in different way. So that I can write it like Wi1, Wi2, and it can be Wik. Now what is this k is? What this k is? So this k is nothing but the neurons in the next hidden layer, just next to the input. So it is something like a weight matrix. Now the thing is, at one time, whenever this 2023 will be at time step 2, and the same value is at time step 6 at the other time. Now the thing is, whenever it will be at t equals 2, or in order it is at 2, definitely the weight matrix will be different for this one, isn't it? So it will be the W2 equals to W21, W22, and it will go up to W2k, while if it is at t equals to 6, it will become W6, and will be something like W61, 62, 6k. Now you can just observe from this example that even for the same statement written differently, for the same word that we are feeding in the feed forward neural network, we are getting a different set of learned weight vector. So if the weight vectors are different, definitely we will be unable to identify whether they are the same word that that is represented in both the statement or both the input, or they are different. But our aim is to figure out whether they are the same word, are they reflecting when I was in Jaipur or something else. So this kind of context won't be clear from the neural network, this feed forward neural network. For that, we need some different kind of provision, okay, where we can learn this context. But the basic problem here in feed forward neural network to learn this context was the different weights that we are learning for the same word, just the order have changed. Okay, so now I hope till now it is clear. So we can make a point here that the thing is, whenever we talk about the context learning, there must be some provision of the parameter sharing. Isn't it? Now, if we come to the presentation, so we are going to talk about the parameter sharing here, as against with the feed forward neural network. Now, we have just talked about what will happen if the parameter are not shared. So in that case, for the same input, we will get different weight vector, and definitely they won't get treated similarly. Now, if we talk about talk in case of if it so if we talk similar in context of CNN, what will be the problem? Or if we talk about CNN versus the model that you have talked about earlier, RNN, the CNN is more toward the spatial CNN, or even we can say for the feed forward neural network, the spatial parameter. Now, the question is, if I ask you from the previous example, if we are having such kind of setup, can we say that there is still some parameter sharing, or is it a completely independent parameters that we are learning? Any answer from your side? So basically here the parameters that we are talking about is it is not completely independent, but it is especially for this part we are having this vector we are going to learn. So it is basically in terms of CNN. If we talk in terms of CNN, so you might have seen that we apply the kernels in the image frames. Okay, so the weight vectors, the kernel matrix itself is shared across the spaces. So the CNN will tell us where that exact that particular value occurs, like suppose some object is there or some lines are there. So the CNN will be able to identify that particular object or that particular uh, word in the image, but it will not get the context of the word, whether I was looking for that word or not. So in the CNN or feed forward neural network, we say the parameter sharing is there, but the sharing is spatial in nature, while whenever we deal with the sequential data, we need a kind of time based parameter sharing. Okay, now how it helps us in sequential modeling. So basically, whenever we go for the parameter sharing, it provides us some advantage of. The first one is, what will happen if we share the same parameter. Suppose in the previous example, if I say that whatever uh, weight vector we had, we are going to use that weight vector over and over again and again. Suppose this is the hidden layers h1 h2, and we are going to share the same weight vector again and again. Okay, so this sharing will help us. So I just write it here. It basically a model example. Okay, different length. So we can say, so in the previous example, suppose the same kind of a statement is there, but it is written the length of the statements are different. So can we apply this example here? Can we apply, suppose somewhere I have written I visited Jaipur in 2023, and somewhere I have written in 2023 I have visited the Jaipur. So suppose somewhere the have is not there, while I have added have in the other statement. So will this feed forward neural network will be applicable? No. So as you have already gone through that, it won't be applicable for variable length input sequence. So, and not only the variable length input sequence, but we need to preserve the dependency of the words across the uh, statement, or we can say the paragraphs. So definitely, to handle these variable length inputs and to preserve the context of what we are learning, we need to go with the parameter sharing. So the first one is we can apply it with the different uh, example of different lengths, and the other one is the dependency okay. So without parameter sharing, it will be difficult for us to basically go for these things. So as we have seen, so suppose we have an input with input picture of 5. Suppose the value of n is 5. Okay, now so for each input we are going to learn different parameter, or we can say weights. Theta 5, or you can say weight 1, weight 2, weight 3, weight 4, weight 5. So this is the input. Okay, and this is the weight vectors or parameters that are learned from input to the next hidden layer. Input to the hidden layer. Now suppose the same statement that I have taken here, if here I have written like I visited Jaipur in 2023, so it is having 5 words. Now for the same, if I say in 2023 I have visited Jaipur, so now how many words are there in this one? So it is 6 now. Okay, so what will happen then? The first thing is the weight learned will be definitely a problem, because the sequencing is now changed. So for the same statement written differently, we are learning, we are updating these weights. And the next problem is, what about the sixth input? Okay, so how we are going to handle the sixth input? Actually, while training, we haven't uh, learned that weight vector, so we are unable to process this extra input. So this is where this basically the motivation of this RNN lies. So let me just go back to this one. Okay, so just move to the, so till now what we have seen, if we are not going with the parameter sharing, okay, so if we are having a different weights like that we have seen here, here this kind of problem will be there. So this will break the idea that the same logic should apply at each time point, because it is the same statement, so it must have the same context. The second problem will be there, like a no generalization. The model will be unable to handle sequence that is longer than or shorter than what is trained during the training phase. Then if the parameters are not being shared over the time, so what will happen? Another thing is, we are learning one weight vector here, a weight matrix here, the another weight matrix here. So the number of parameters will be higher in case of non-shared parameter models. Okay, and the one that we have talked about is that if we are trying to learn some context, so that we will be unable to basically learn the temporal dependency between the wording. Okay, so it will simply be behaving like kind of feed forward layers. Okay, so the thing is, if we visualize here, so just look at here, we are having a feed forward neural network, and the other one is the recurrent neural network. Okay, so here we are you have already talked about this kernel, how kernel works, how the feature extraction is applied. So definitely it is spatial in nature. The same kernel, if you have gone through the kernels, the concept of kernels, so we have uh, seen we have several kernels, and each of the kernel will learn different kind of features. Okay, so definitely this one kernel will learn one kind of feature, like suppose it is learning for that particular year, so it will learn wherever that 2009 or 2023 appears in the input, but it will not be able to learn how that 2023 or 2009 will be related in the context of whole input. Now, in case of RNNs, what we do, we basically use the same weight vector across the time across the time unit. Okay, so basically this is what we have talked till now. Okay, so let me just go okay, so in RNN what we do is, we have the same concept. We have input, okay, we have output, okay. But the thing is, rather than learning a different set of parameters, what we are going to do is we are going to share the weight vector again and again. We are going to recursively we are going to use the same set of weight. Suppose this is the function that we are learning. So this function will be will take the same weight vector whatever input sequence we are providing, okay. So we will just look around this unrolling of this one. So let me just go through the next thing. So let me come to this point later. So the one thing is, whenever we talk about the time step, so this time step need not be the actual time. It is just the sequencing that we are concerned with. We are not strictly sticking with any times, okay. It is just the sequence in which the input is being provided, okay. Now if we talk about how this RNNs look like, so it is somewhat similar to what we have talked about this feed-forward neural networks. So we have this hidden layers, we have this hidden layer, but the way we are going to work with this hidden layer and the way we are going to use the parameters across the hidden states is different from that of CNN. So a CNN or that feed forward networks. So basically in the CNN and feed forward networks, the parameters are specially shared, but in case of RNN, we are going to share it over the time. So the same weights will be again and again, they will be reused, okay. So these are some applications of RNNs that you may have. So the vanilla neural networks are like this one. We have the hidden layer, we have input, and then we have some output. Okay, so a classification report or the predictions. Okay, then the other one is just image captioning. Okay, so image captioning, we are going to just generate for each frame. Just by looking at the frame, we are going to generate some caption of the image. So then sentiment classification, the machine translation, and there are many more applications than what I have basically listed here, okay. So if we talk about the RNN, okay, so basically this RNN is we can treat it like this one. So we are providing the input, we have one RNN cell or the function, and that is going to recurrent over the time, okay. And each time we can also get some output. So in the previous slide here, there are different variants. We are providing the input, at each time we may have some output, or the output may be generated at the final step, or we may have some delayed output, okay, or the parallel output, okay. uh, so this output can be modeled from any of this example. Now if we mathematically formulate this model, so it is nothing but we are trying to figure out what the state of this RNN is, okay. What this what I'm saying is this RNN is just some kind of function, okay. And this function is nothing but we are having some. So this recurrent, let me just draw it here. So what I was saying here is, so it is some kind of suppose it is something like, so it is input at time step t, then we have a function and we have a output, okay. So we are talking at time step t. So this f can be modeled as, we have one input. Now, as in case of feed forward and CNN, we have some weights here. So let's suppose I'm writing this weight as u. This u is the input vector corresponding, this weight vector corresponding to this input. So it will be something like uxt. Okay. And then what we are having, we are considering what we have basically seen earlier. So that suppose I am saying that is represented by st. St is some previous state information or previous information. Like suppose we are learning something. Okay. So whenever we are learning something, so whatever we have learned till now, we are also using that concept to come with the conclusion for the current derivation or current finding. So we are also going to provide the previous learnings. Okay. Now, apart from that, we are also having some weight vector that can be assigned for the output. Okay. So it is similar to that what we have talked about the CNNs. So this is one weight vector, this is another weight vector. But the thing is, we are going to use this weight vector again and again, the same weight vector again and again, even we unfold it across the time. Okay. So just come to the PPT. We will again come back here. So here what we are going to do is, this theta indicates the weight. Okay. Now this is the previous state history. This is the current input that we are going to do. So whenever we are saying that we are going to learn the context, we are talking about the previous state information. Without that previous state or previous knowledge, uh, in the current state only, there is no meaning of making the context learning. Okay. So it can be rewritten like this one. So the RNN is being modeled as some input from the previous knowledge and the current input. Now these both will be acting as, so it is something like the previous knowledge, the current input, your output, and then recurring over the time. This is the RNN. Okay. So if we unfold this this particular RNN architecture, so it will be something like this one. Okay. We are not concerned for the timing, we are not concerned about the input, we are just concerned about the previous knowledge that we have. So what we have, suppose at time 3, or suppose I have some word I want to learn, something like this one. So suppose we are at suppose I've written this, or I visited okay. Suppose I just want to learn what word will be here, what word will be placed here, or something, what word will be predicted next based on what we have learned. This will be attained through this RNN. Like, just imagine, just we are just unrolling uh, the previous diagram, this recurrence formulation. So what we are going to do, suppose this is at 1 2 3 4 5 at fifth step. Okay. So it is like something like, if I talk about example, we are not concerned with the input, so we are just talking about the that weight vector or the theta. You can write it as weight also. Okay, no issue. So we are not talking about the weight vector here. The next will be again the S4 had some context previously learned, so it will be f of S3 and then some theta likewise. So we are going to recur this equation, and if you are familiar with that Fibonacci series and factorials in C programming, this looks like similar to that one only. Okay, so we are recurring over the same formulation. So the parameter is going to be shared across. So if we are talking about the theta, so if this is the theta, the same theta is going to be applied here. There is no separate theta here. Means we are using the same weight. Means let me just write it here. Suppose these are the inputs. This is the RNN cell. Suppose I have provided I. Okay, so this is the input. This is, we can say, this is the embedding, or embedding we can say. Now suppose I have provided the first input I, so it is xt or x1 we can say. Okay, at x2 I am providing visited. So what will happen? So this was u that we have seen. There will be one output and that will be v. Okay, now the thing is, suppose and suppose some S0 is there. As we are talking about the time one, suppose previously it was, the previous knowledge was S0 and that we can set it as 0. Means there was no knowledge at all. And then for this one also we need some weight, the weight vector. Okay. Now once we have provided this I to this function f, so suppose this function is f. Now the next thing will be the function will basically take these two inputs, and then whatever it will compute will be output. The output multiplied by this weight vector will become output. Now we are going to share the same weight vector as it was here, and whatever it computes will go to the next hidden state. So sometimes it may be represented at h t, and we can write it like h0. Okay, so the information that that was previously there, so this is h1 now. Okay, now when I will provide this visited next time, what is going to happen is, the next time this will be the u only. Okay, this is going to be v, this is going to be output. Here the thing is, this function will now learn something like we are providing the x2 u and the htw. Okay, and based on that it will give you the output as well as the next hidden state, that is, so it will be h2. Okay, something like that. So it will go on unfolding over the time as we are going with the sequence of input. Okay, so this is simple example without any input. We are just considering this part, okay, without we are not concerned about, for the time being, we are not concerned about this one. We are only talking about this unrolling. Okay, so this is what is referred here. Now, this is what we are talking about as a whole. Now, as a whole, now this is what this RNN looks like. So we are having some input. Now we have incorporated the input also. Okay, so this is the RNN network that we have, and that we are going to unfold over the time. Okay, so now, so I think this is over. So the problem with the RNN is, can you just tell me what problem we may face here? Anyone? Can you tell me what kind of problem we can face here? Anyone? What kind of problem we are going to have? Okay, so definitely if we look around this one, so as we are going to move along the input sequence, and if the input sequence is very longer, okay, so for that we may face a problem of a very problem that is vanishing gradient. Okay, so like suppose if I say lack of attention, no, not exactly. Actually, it will be something like we are dealing with long sequence, and the deeper the sequence will be, the more dependency preservation will be there. But the problem will be, if we have a longer sequence, if we are going with very longer sequence, okay, so at the time, so as we all know that RNN work back propagation through time. So if we are go on, like suppose one example, the kind of, suppose we are saying something to next person. Suppose there are a series of person here, okay, and they are saying something to next person. Okay, now as the knowledge will move from this end, means whatever knowledge is there is moving to this end, the learning, whenever the learning will happen and the parameter is going to be updated, definitely it will go on decreasing, or the value will be disseminating over the time. So that the one problem that will be the vanishing gradient or exploding gradient. So let me just write it simply. Mathematically we can write it something like this one. Suppose we are ignoring the input and any bias. So suppose we are having the, sorry, ht minus 1. Okay, suppose we are having something like ht, the hidden state, this one. So ht is nothing but, we can say this is the ht. Okay, now if we say in forward direction, it is going to be like just a series of function, like we have just seen here, a series of function, isn't it? This is going to be nested again and again. Now if we talk about the same thing for this one, what will happen then? So the f is something like w h t minus 1. I'm ignoring the basically the input here or any bias. So it can be further written like f of w h t minus 2 and so on. So if we talk about ht, so what will happen then? What will be the value of ht? So from the beginning, if we talk about from 1 to t, so it will be something like w t times, and finally it will be the h0. Is it clear to all of you how this is happening here? Any doubt? I hope it is clear to all of you. So what we are going to do is here, next is, so now what this W is. So W is nothing but the weight vector, isn't it? Now, if we suppose that this weight is, the weight vector can be diagonalized. Okay, so we can break it in form of that Q inverse Q inverse. Okay, so this is the eigenvalue vector and this is eigen vector, isn't it? Now this is the diagonal matrix. This is the diagonal matrix only. Okay, now this is the eigenvalue lambda. Okay, now the thing is, there are two cases. If the lambda I is less than 1, or lambda I is greater than 1, or lambda is equal to 1. So if this lambda will be less than 1, this is called the vanishing gradient. While what will be this one? Because this is going to be multiplied. So if I say Wt, what will happen? What will be the value of Wt? Can anyone compute this value of Wt? So this expression is the expression is, this T is not transpose, it is T times, as we are talking about this Wt. So now anyone can ask me why this Q is not T times. So can you tell me why this Q is not having something like this? Why this is not having something like T? Huh? Anyone? So it is just a mathematical expression that you can solve and you can get it through. So suppose I am writing it for W2. So it will be something like, so if you will break it down, it will be, so not T, actually if I write W, it will be diagonalized as Q inverse. So it is something like that. So it is actually, it is a general form, it is not the value of W. So okay, so it will be Q inverse and it is Q, then it is Q inverse. So it is going to be identity matrix and this will be 2 and Q inverse. So you can generalize it. Okay, generalize it to this one. Okay, so this is the vanishing gradient problem, this is the diagonal values, and this is exploding gradient and no learning at all. Okay, the gradient won't change over the time if the lambda is identity matrix, the diagonal matrix with values 1. Okay, so anyway, so next, so the problem with this RNN is the one thing, the vanishing gradient and the exploding gradient. So the solution to this problem is basically we can have the problem was the vanishing gradient problem was due to the fact that we were carrying the state information, sorry, the state information state information over the time, isn't it? So rather, we can just drop some of the information over the time step so that it won't get overloaded by the previous history information. Okay, so that is the main idea behind this uh, LSTM. So basically, to handle the problem of RNN, we are having three different concepts that we include. The first one is the selective write, the selective read, and selective forget. Okay, so whenever we are passing the information, whenever we are carrying the information from previous step, whenever we are uh, considering the information from the previous state, how much information should be passed to the next one, and how much information I should write on the uh, memory, means how much long term and short term memory should be kept uh, along the time. So that is basically attained through these three mechanisms: selective write, read, and forget. Okay, so let me just go through a simple a model. Okay, so whenever we talk about this selective read, write, and forget, so for that we have provision of input, output, and forget gate. Okay, so in order to apply the concept of input, actually selective, the three objective that we want to apply on the RNN is selective input or selective write, sorry, selective write, forget, and read. Now in order to apply this concept, we have means that LSTM has introduced this concept is applied to LSTM. Now LSTM has also introduced the gates. The gates. So basically the RNN variants, the LSTM is one of the variants that we are having. So apart from that LSTM, so whenever we talk about the drawbacks of RNN, okay, so the problem whatever we have faced, whatever problem we have faced can be basically solved in different ways. The one is the gated RNNs. We may apply the skip connections, and there are many other techniques that we can apply, like the modern techniques are attention and transformer mechanism. Okay, so later on in the series of this FDP you will learn about the attention and transformer. So but the time being we are having this LSTM. So the one a very predominant model that is basically a kind of RNN variant is gated RNN, and in this one we talk about the LSTM and the GRU. Okay, so in case of LSTM we are having these three concepts, means the LSTM says that in RNN we were having all the information along the way. So rather than having all the information from the beginning to the end, can we just keep on minimizing the information that we are carrying along the way? Suppose you are reading some story, okay, and in order to get the gist of the story, definitely you are not going to remember all the thing through the chapters that you are going through, but you are only carrying the important information that will help you to make the decision or conclusion at the end. So this is the basis, the basis of the LSTM. So this is the gated RNN. So the purpose of gates are to control the amount of information through the network. Okay, so basically now, so let me just draw a simple diagram here how it works. So here in case of LSTM we are having two things. One is the long term memory and the other one is short term memory. Okay, now this long term memory, long term, we can indicate it as the cell state. Okay, and the short term is basically indicated as the hidden state that we just talked in the previous slide. Okay, now just a simple diagram how this gates work, how this LSTM looks like. So basically we have three gates: forget gate, the input gate, and the output gate. Okay, we have this input at time step t. Okay, here we are having the cell state h t minus yes, the previous state, and this is the short term. This is the short term memory, means the memory that is coming coming from just before the this cell. Okay, and the another one is basically that is the long term memory. Long term memory. Okay, so we are having three gates. The forget gate is basically tells us how much information. So this is the multiplication sign. Okay, how much information to basically preserve from the long term memory. Okay, so basically whatever memory that has been carried from a long way, so this forget gate says how much information should be propagated in this propagated to next one. Okay, so this is the forget gate, while the input gate is basically the one that will tell us. So basically again everything will remain same. This is the inputs. Okay, and now the input gate, what it will do, the input gate will decide basically that how much information from this current cell state will be basically added to the long term memory. Okay, this is the one part. So input gate will tell us, we will continue with this one in the next lecture on this particular one. So it will just take half an hour or 40 minutes to cover all the LSTM and GRU. Once it will be clear, once this part is clear, everything will be clear to you. So basically the other thing is, the first thing is how much information from the long term memory should be contributed for this cell state, and this will tell us whatever information you have generated. So this is a single RNN cell. This is a single RNA cell I'm talking about. So whatever information it has generated, how much information from this cell state will be contributed to the long-term memory, and finally applying this information and this current state value, the output gate will generate the next cell state, the short-term memory that will be fed to, that will be basically fed to the next RNN cell. Okay, so we will continue from here in the next class. Okay, so for the timing, just let me know if you are having any doubt till now. We may just talk about that one, and we will continue from this one. There is nothing more left. If you have got the concept till now, so let me know if you are having some doubt how to decide what is important. Okay, so anyway, the thing is, whenever we talk about the weight vector, so like what we had in the CNN and that feed forward neural network, the same way we are decoder latent space learning fit in our RNN. So RNN is so let me first answer to your first question. How we decide what is important? So it is all about the parameter or the weight vector that we are learning across the time step. So if we see here, across the time step, we are learning the same weight vector. Okay, we are not changing the weight. So whatever sequence we are feeding in, all the sequence will have impact on this weight vector only, or the parameter only. So all the context will be learned by this weight parameter. So that was not in case of the CNN and what we say FFN. So there we had different weight vectors, so the context was not basically learned. So this is the concept. The basis behind this one is the sharing of parameter. The parameter sharing is the basis of how it basically learns what is important. So not only what is important, it also learns the context. Now the encoder decoder, so basically encoder decoder, we can say here also it is a kind of encoding. If we see here, we are feeding some input here, okay, and that input is going to be encoded in some output. Okay, so some way or other way it is somewhat encoding, but we are not going to talk about decoding here. We are not concerned about the decoding here, but definitely the encoding can be basically analogous to what we are seeing here. So we are providing some information, the function is applied, and the input is encoded in some different some output. Okay, now the next question is, sir, kindly take a sample sentence and explain through the diagram in next slide. Definitely I will take. Actually in this slide that we are seeing, we will talk about this example with one sentence in the next lecture. Definitely just work around this example. Okay, we will work around this example in the next class, and we will see how it works. And definitely after completing the next lecture, you will not have any doubt regarding this LSTM, that I guarantee. Okay, if it is clear till now why this RNN, why LSTM is there, so the basic reason of this LSTM is how we are going to control the information. So the gated recurrent networks are the basic idea behind this LSTM and GRUs. Means in the RNN there was no control over the how much information we are going to flow to the next hidden layer or next hidden state. So the LSTM has introduced some gated mechanism that will control how much information we are going to flow through the network at each time step. So I hope till now it is clear. Definitely in the next class we will be covering with some a sentence. We will take some sequence of word as an example, and we will cover this concept LSTM and GRU. And definitely I guarantee this concept will be very easier once we will see the next lecture. So it might be something something might be going into your mind, like what are the things that we have left, or what we need to cover. So you don't have to bother about, just look around what I have just uh, discussed, and everything will be fine. In the next class, we will see the LSTM. Any more question if you have on what we have just studied, discussed? Anyone? So I think there is no more question. So thank you all. We will be meeting in the next lecture. There we will continue with the GRU is a very small topic. Once the LSTM is done, it will take 5 to 10 minutes to cover the GRU. So anyway, thank you all. Thank you for joining. And the next session will be starting just after 15 minutes. So it won't, it might not be starting from 11:15. Okay, so we will be starting from 11:25. Okay, so thank you. So next session we are starting at 11:25.
Yes, sir. Thank you, sir. Thank you for such wonderful lecture.
Thank you so much.
So next session that we will start at 11:30. So I will post this message in a group.
Okay, okay, sure, sir. Okay, sir. Thank you, sir. Thank you all the participants.